Today we're going to look at collision theory, which we've actually lightly talked about before during this chapter, but never actually used those terms. In order for a reaction to occur, you need to have the reacting molecules collide with one another. If one molecule stays on one side of a dish and the other molecule stays on the other, how would you ever make your products? But they can't just collide and that's all. They have to collide with enough energy to break the original bonds that might be holding those molecules together in order to form new bonds. And the orientation is also important. Like you could see here, if we're trying to make this nitrogen monoxide molecule and an ozone, if the molecule collision is ineffective, we don't actually make products. We start with nitrogen monoxide and ozone and end that way. But if we were trying to make an NO2 molecule, an oxygen, let's say, we need the correct end to hit that nitrogen monoxide molecule in order to make it turn into its products. If your reactants are moving too slowly towards one another, the molecules might bounce off of each other with no reaction. If they're not facing the right way, again, they might bounce off of each other with no reaction, but as long as they have enough energy and they're oriented correctly, that's when something's actually going to happen. Your concentration and reaction rates are often related to one another. Generally speaking, if you have more particles, they'll run into each other more often and have a faster rate. It doesn't always happen that way. You might have a zero-order reaction where even doubling the concentration of a chemical has no impact on the rate, but oftentimes more concentrated stuff leads to faster reaction rates. Temperature also often has an effect on the reaction rate. Reactions tend to happen faster at higher temperatures because you increase the average kinetic energy of the particles. So there's a greater percentage of particles with a sufficient enough kinetic energy that when they collide with one another, they're able to make products. They're able to break those original bonds. Here's that Boltzmann curve that we looked at earlier in the year. And when you have a lower temperature substance, you have a greater number of particles at that lower temperature. Higher temperature, it kind of spreads out a little bit. So let's say this vertical line right here represents the activation energy, that quantity, whatever that corresponds to on the x-axis, that's the activation energy for a certain reaction. And so when you have molecules at a warmer temperature, we have a greater number of particles underneath that curve that are able to meet the activation energy requirement, whereas if you have a colder temperature, there's a smaller percentage of the molecules overall that have enough energy within them with that kinetic energy in order to break the original molecules. As far as orientation goes and how that affects reaction rates.
Jim Heron, please come to the main office. Jim Heron, please come to the main office.
Sorry guys, obviously recording this at school. The molecule orientation can also affect reaction rates. As you could probably imagine, if you had a really big or complicated molecule and you need proper orientation for the reaction to work correctly, then if you have that big or really complicated molecule, it's hard to get it lined up just so. So you're probably going to have fewer molecules percentage-wise that are able to meet that orientation requirement, and so the reaction overall tends to be slower. Reactions that have small activation energies tend to react quickly because a lot of molecules have enough energy to react, whereas if you have a large activation energy, those tend to be a little bit on the slower side because there's not a ton of molecules that reach that energy barrier. Here's an example of an exothermic reaction where we have our reactants in the beginning, our products at the end. So you can see here's your activation energy in the forward direction, A turning into B. And this activation energy mountain is relatively small compared to the reverse direction where B is turning into A. That mountain is taller. And so if we had to predict the rate of the forward reaction versus the backwards reaction, the forward reaction is probably going to be faster overall compared to that reverse reaction. Here, the opposite would be true. Here, this mountain is taller, going in the forward direction, A turning into B, then B turning into A. This mountain is smaller overall. When you have a catalyst, it reduces the height of that mountain. The activation energy, the amount of energy required to get over and turn into products, is less. And so we're able to get to the product side faster. So the job of a catalyst is to show the reaction, basically another path, a shortcut to get to the product side in a shorter amount of time because they don't have to expend as much energy to get there. This equation on these last couple slides here, called the Arrhenius equation, is no longer on your equation sheet. It used to be years ago, but it shows a correlation between your rate constant, K, activation energy, E sub A, how frequently your particles are having collisions, and a gas constant and temperature. You could see all your variables there. So while you will not have to solve for anything like this mathematically, I think it just is nice to show you guys that there is some kind of mathematical relationship between the rate constant and activation energy. And because there's that correlation mathematically between activation energy, rate constants, and temperatures, that equation would allow you to find the third variable if you knew the other two. Like I said, you're no longer going to have to do anything mathematically with it, but I think it's just helpful for you guys to see that there is some kind of mathematical correlation between all those variables.